Uh, our topic is all about CMOS process technology, and under that is layout design rules. So what is layout rules? It is also called design rules, and the main objective of the layout rules is to build reliably functional circuits in as small as an area as possible. The rules are defined in terms of feature, size, or widths, separations, and overlaps. And it is important to note that design rules do not represent some hard boundary between correct and incorrect fabrication. They represent a tolerance that ensures high probability of correct fabrication and subsequent operation. In Chapter 1, it describes the rules of the MOSIS-CMOS scalable rules. The MOSIS rules are expressed in terms of lambda, and these rules allow some degree of scaling between processes, as in principle, you only need to reduce the value of lambda and the designs will be valid in the next process, down in size. So, under the layout rules, the design rule background, the well rules, transistor rules, contact rules, metal rules, via rules, and other rules. Well rules. As you can see in the figure, the CMOS N-well process transistor and well substrate contact construction. Next. The N-well is usually a deeper implant than the transistor source drain implants, and therefore, it is necessary to provide sufficient clearance between the N-well edge and the adjacent N-plus diffusions. Under the transistor rules, the CMOS transistors are generally defined by at least 4 physical masks. These are the active, or also called diffusion, N-select, also called implant, P-select, also called PEEP implant, and polysilicon, or also called poly. The active mask defines all areas where either N or P-type diffusion is to be placed, or where the gates of transistors are to be placed. The gates of transistors are defined by the logical end of the polysilicon mask and the active mask, where polysilicon crosses diffusion. The select layers define what type of diffusion is required. If N-select surrounds active regions where N-type diffusion is required, P-select surrounds areas where P-type diffusion is required. The N-diffusion areas inside P-well regions define the NMOS transistor or the N-diffusion wires. And the N-diffusion areas inside N-well regions define N-well contacts. And likewise, P-diffusion areas inside N-wells define the PMOS transistor, and P-diffusion areas inside P-wells define the substrate contacts or the P-well contacts. So next is the contact rules. There are 4 kinds of contact rules which are the following: metal to P active, P diffusion; metal to N active or the N diffusion; metal to polysilicon; and metal to well or substrate. Because the substrate is divided into well regions, each isolated well must be tied to the appropriate supply voltage. The N-well must be tied to VDD, and the substrate or P-well must be tied to ground with well or substrate contacts. So this is a substrate contact. And in the mass summary, the only mass involved with contacts to active or poly is the contact mass, commonly called or CA. Contacts are normally of uniform size to allow for consistent etching of very small features. The next one is the metal rules. Metal spacing may vary with the width of the metal line, so-called fat metal rules. That is, above some metal wire width, the minimum spacing may be increased. This is due to etch characteristics of small versus large metal wires. Metal rules may be complicated by varying spacing dependent on width. As the width increases, the spacing increases. Metal overlap over contact might be 0 or non-zero. Via rules. Processes may vary in whether they allow stacked vias to be placed over polysilicon and diffusion regions. Some processes allow vials to be placed within these areas, but do not allow the vials to straddle the boundary of polysilicon or diffusion. Vials are normally of uniform size within a layer. They may increase in size toward the top of a metal stack. For instance, large vials required on power buses are constructed from an array of uniformly sized vials. So, last but not the least, the other rules. The passivation or overglass layer is a protective layer of silicon dioxide that covers the final chip. Appropriately sized openings are required at pads and any internal test points. Next. These are the other rules. The extension of polysilicon or metal via no-contact or via differing gate poly extension depending on device length, maximum width of a feature, minimum area of a feature, minimum notch sizes. The next part of the layout design rules are scribe line and other structures. So what's scribe line? Scribe line surrounds the completed chip where it is cut with a diamond saw. The construction of the scribe line varies from manufacturer to manufacturer. It is designed to prevent the ingress of contaminants from the side of the chip, as opposed to the top of the chip, which is protected by the overglass. The several other structures are included on a mask, including the alignment mark, critical, dimension, structures, vernier structures, and process check structures. So, under the layout design rules is the MOSIS scalable CMOS design rules. MOSIS once offered a wide variety of processes from 2 micrometer to 180 nanometer, compatible with the scalable CMOS rules. Indeed, MOSIS also supports 3 variants of these rules: SCMOS, SUBM, and DEEP, which are progressively more conservative to support feature sizes down to 180 nanometer. Chips designed in the conservative DEEP rules could be fabricated on any of the MOSIS processes. The micron design rules. In the table, the hypothesis MOSIS scalable rule is 65 nanometer rule. Next. So, the next subtopic of the layout processes technology is the CMOS process enhancements. Under that is the transistors, interconnect, circuit elements, and beyond conventional CMOS. So, in transistors, the following are the multiple threshold voltages and oxide thicknesses, silicon on insulator or SOI, high K constant gate dielectrics, higher mobility, plastic transistor, and high voltage transistors. In the multiple threshold voltage and or oxide, some processes offer multiple threshold voltage and or oxide thicknesses. Low threshold transistors deliver more on current but also have greater subthreshold leakage. Providing 2 or more thresholds permits the designer to use low voltage devices on critical paths and higher voltage devices elsewhere to limit the leakage power. In the silicon on insulator, a variant of CMOS that has been available for many years is silicon on insulator, SOI. As the name suggests, this is a process where the transistors are fabricated on an insulator. SOI stands in contrast to conventional bulk processes in which the transistors are fabricated on a conductive substrate. 2 main insulators are used, the silicon dioxide and sapphire. So this is the SOI types, the sapphire and the substrate. The one major advantage of an insulating substrate is the elimination of the capacitance between the source-drain regions and body, leading to higher speed devices. Next one is high constant gate dielectrics. Metal oxide silicon transistors need high gate capacitance to attract charge to the channel. This leads to very thin silicon dioxide gate dielectrics. Gate leakage increases unacceptably below these thicknesses, which brings an end to classical scaling. Simple silicon dioxide has a dielectric constant of 3.9. Gates could use thicker dielectrics and hence leak less if a material with a higher dielectric constant were available. Next. Last but not the least, the higher mobility. Increasing the mobility of the semiconductor improves drive current and transistor speed. One way to improve the mobility is to introduce mechanical strain in the channel. This is called the strained silicon. This is the strained silicon transistor micrographs, which is the NMOS, the strain, and in the PMOS, this part. Plastic transistors. The transistor is built upside down with the gold gates and interconnects patterned first on the substrate. Then an organic insulator or silicon nitride is laid down, followed by the gold source and drain connections. Finally, the organic semiconductor or the pentacene is laid down. This is the plastic transistors, the substrate, the insulator, and the semiconductor. High voltage transistors and high voltage MOSFETs can also be integrated onto conventional CMOS processes for switching and high power applications. Gate oxide thickness and channel length have to be larger than usual to prevent breakdown. Specialized process steps are necessary to achieve very high breakdown voltage. So the next topic will be the interconnect. Interconnect has advantaged rapidly. While 2 or 3 metal layers were once the norm, CMP has enabled inexpensive processes to include 7 or more layers. Copper metal and low constant dielectrics are almost universal to reduce the resistance and capacitance of these wires. Next. So, under the interconnect is the copper Damascene process and the low constant dielectrics. So, in the figure, the copper dual Damascene interconnect processing steps. The first is diffusion barrier etch stuff via dielectric, line dielectric, anti-reflective layer, dielectric etch, T barrier, copper seed, and copper fill, and CMP. Next. The low constant dielectrics. Silicon dioxide has a dielectric constant of 3.9 to 4.2. Low constant dielectrics between wires are attractive because they decrease the wire capacitance. This reduces wire delay, noise, and power consumption. The circuit elements. Since the CMOS transistors provide for almost complete digital functionality, the use of CMOS technology as the mixed signal and RF process of choice has driven the addition of special process options to enhance the performance of circuit elements required for these purposes. Next. So, the under circuit elements are the capacitors, resistors, inductors, transmission lines, bipolar transistors, embedded DRAM, non-volatile memory, fuses and anti-fuses, micromechanical systems, MEMS, integrated photonics, and three-dimensional integrated circuits. So, the circuit elements, fringe capacitor, this is the resistor layout for the CMOS. Spiral inductor and its equivalent circuit. In the transmission line, microstrip and coplanar waveguide. Vertical PNP bipolar transistors and its representative layout. This is a non-volatile memory. Next. A typical metal fuse and the E-fuse, the intact and blown. This is the integrated photonics, optical waveguide, and holographic lens integrated with the 130 nanometer CMOS process. And this is the 3D IC or the three-dimensional integrated circuits. Next. Last topic of CMOS is the beyond conventional CMOS. The gate wraps around T sides of the vertical source drain fins. The width of the device is defined by the height of the fins, so wide devices are constructed by paralleling fins. So this is the fin. This figure shows the micrograph of a prototype FinFET that Intel calls a tri-gate transistor. So this is the FinFET structure in cross-section top view. Next. So, carbon nanotubes are one nanotechnology that have been used to demonstrate transistor behavior and build inverters. Nanotubes are cylinders with a diameter of a few nanometers. They are of interest because the nanotube is smaller than the predicted endpoint for CMOS gate lengths and because the nanotubes offer high mobility. So this is an example of a carbon nanotube transistor. That's all. Thank you.